The final recursive sort that we're going to be looking at is called radix sort. Now, radix sort is one we've seen before, and essentially it's actually an O of n sorting algorithm, but the constraint is that we can only do it on lists of non-negative integers. Now, as we said before, the fastest sorting algorithm we can do is O of n log n if we don't know about any special information. In this case, we know that it's non-negative integers, so then we can do it in O of n. Now, let's look at the actual code. So the way that radix sort works is that essentially you look at the first digit and then put it into buckets in order. Then you take them all out in the order that you put them in, and you look at the second digit and put them into buckets of 0 through 9 based on the second digit. And then you take them all out in the order you put them in and look at the third digit. Put them into buckets from 0 to 9 based on the third digit. And then take them out. And eventually when you end up running out of digits on the longest number, you'll know that it's all sorted. Now, in a way to get around the fact that you need 9 buckets is that if you think of the numbers as being in binary, that means that the representation that they have is zeros and ones, which means that when we look at the 0th digit in binary, there's only 2 buckets. Either it's 0 or it's 1. And so that's exactly what we do here. So what we do is we do radix sort on a list, and this is a function defined inside of the function, which essentially is going to do the actual sorting. Now what we have is what we call the digit selector. Now there's a few things that we have to learn before we can understand this code. Now in binary, we have stuff called bitwise operators. Now let's say that I have the binary 100100. Now there's a few things I can do. First thing I can do is shift this over by some number, let's say 1. This will result in 100100. You can think of the shift as if we were multiplying a number in base 10 by the number 10, because this essentially puts a 0 at the end. Oops, it's 0. So if I shifted 100100 over by 2, I would get 100, Now, secondarily, we can also do something which is the AND operator. So let's say I do 100, 100, and 100. This will essentially compare each bit in the same digit place and say if they're both 1, it'll be 1. If they're not both 1, then it'll be 0. So in this case, 0 and 0 is 0. It goes to the second digit place. 0 and 0 is 0. Then it'll go to the first digit place. 1 and 1 is 1. And then if there's nothing left over in the number, it'll be implicit zeros, so then the rest will be zeros. So, as we notice, if we AND something by everything zeros except for 1, 1, then it'll basically be telling me if at that location in the binary number, is this digit a 1? Because notice how it was a 1 in this case, but let's say that there was a 0 here. Then it would be 0 and 1, which would actually just be 0. So it's basically, if I AND it by a single 1, then it's telling me if the number is actually a 1 or a 0 at that location, which will be really important for radix sort because we want to be able to say if at the current digit that we're looking at, is it a 1 or a 0. Now, additionally, we have to understand that, let's say that I start out with 1. If I right shift it over by 1, I end up with 1, 0. 1, 0 right shifted over by 1 ends up with 1, 0, 0. And 1, 0, 0 left shifted over by 1 ends up with 1, 0, 0, 0. So as you can see, if we keep shifting 1 over by 1, then we keep increasing the number of zeros. So what we're going to do is start with 1, and the digit selector is basically going to be a number which is in binary, all zeros except for 1, 1. And initially it's going to be 1. So imagine if I took the number 1000111 and I ANDed it by 1. This would basically tell me if the 1's digit was a 1. In this case it is. However, if I did 010010 ANDed by 1, it would be 0 because it's the 0 and 1, which is 0. So essentially what I'm going to do is say, okay, let's look at the recursive case. The things with zeros in them is every number in L if x and the digit selector is equal to zero. That means that at that digit there's a 0. The ones is if I say x and the digit selector is not equal to 0. That means that it's a 1 there. So then I've partitioned it into zeros and ones for that given actual digit. And so then I recombine the lists in order, and I say digit selector left shift by 1. So then I started out at 1, and I left shifted over by 1, and I start out at 1, 0. So the next time I do digit selector, it's basically going to be checking the second digit in binary. So in this way, we can basically keep shifting over which digit that we're actually going to be checking, and keep partitioning it into 2 buckets, and then checking the next digit. Now, we know that we're done when the digit selector, when it says that we're done when the digit selector is greater than the max value. Now, the reason this is because what this digit selector actually represents. So 1 in binary is just 1. 1, 0 in binary is actually 2. 1, 0, 0 is actually 4. 1, 0, 0, 0 is actually 8. So you should be seeing a pattern that we're actually shifting over the number. Whenever we shift the number over by 1, we actually multiply it by 2. And so these digit selectors are all powers of 2. And so we know that we're done because in binary, for this given length of digits, the largest possible number is going to be the 1 in the front. So if we've gotten the max of L, we want to basically say, okay, have we reached a number? Is our digit selector greater than the max value? That means that we've probably checked all the digits inside of L, and so that we're done. So we know that we've checked all the digits and put them into the buckets and done this whole thing recursively. And so we essentially know that we're done, and we return L because it's already sorted. So if I try to radix sort this list, then lo and behold, it sorts it. So radix sort is a very complex algorithm, and especially when we add in these binary operators, it gets a lot more confusing. And then it doesn't help on top of that we're adding in recursion. However, you should try and convince yourself that this is true by first making sure that you understand the way these bitwise operators work, and then making sure by tracing over this code on a given input that it's doing what you expect. So this is radix sort.